Let's start off with a derivation of the springs in parallel and how we get that weird sort of relationship there. So let's design our system. So we've got one spring and another spring connected together, and we pull them that way with some force F. Now let's say that they don't necessarily have the same spring constant. So let's say this is K1 and this is K2. Now, the outcome of this will be is that they must, because of the way the system is designed, they must extend to be the same length. Okay, so the extension X is the same for both when we've applied this force. So what we can do is we can say, okay, so we've got that the force is equal to the effective extension, so effective spring constant multiplied by the extension. And what we have for both individual ones is we know that this one is going to have is going to take a force of K2 times the extension, and this is going to take a force of K1 times the extension. So we can apply Hooke's law to each of them in turn. So given that this force, total force, so this is the equation for the total one, we can also say that if we call that F2 and this is F1, so we say that that force, the total force, must equal the sum of the individual forces, okay, depending on how they split. And we can just therefore compare the two. So we can say that the total force has to equal the effective spring constant times by the extension, which is also equal to the F1, which is K1X plus F2, which is K2X. Given that the X's are all the same, we end up being able to, we can just sort of cancel them out because there's an X on each part of the thing. So we end up with the effective stiffness is the sum of the individual stiffnesses. And if they are therefore the same, if K1 and K2 are the same thing, that would just be, if K1, K2, you would just end up with equals to K1. So if they are exactly equal. And that's how we end up with that derived for a spring system in parallel. What about springs in series? Well, let's draw our little diagram. There's spring 1, which is a spring constant of K1. Then spring 2, which is a spring constant of K2, and we apply a force. Now in this case, what is constant is not the extension. In this case, the force the force across each spring is equal to that total, that singular force. They both get pulled by the same amount because of the way the forces go through. So, and what we have is the total extension so X total is going to be the extension of spring 1 plus the extension of spring 2. So we can look at Hooke's law overall. For the overall system, we can say that the force is equal to the effective spring constant times by the total distance. And we can also look at the fact that therefore that is equal to xt, that the total extension is equal to the force over the effective spring constant. So that's looking at the overall system. If we look in each one in turn, we would say that x1 is going to equal the force over the spring constant of spring 1. x2 is equal to the force over the spring constant of spring 2. So what we end up with is that we can therefore, given that this plus this is equal to this, we can generate this relationship. We can say, therefore, that equals x1 plus x2. So the force over the effective spring constant is equal to the force over K1 plus the force over K2. Given there's an F everywhere, we can divide through by F, and what we end up with is 1 over the effective spring constant equals 1 over constant 1 plus 1 over constant 2. Now, why, this is a bit of a trickier way to handle this because it's not quite immediately so obvious what occurs, but what we can do is say, okay, what if K1 equals K2? So we can just set them both equal to K1, and we would say, okay, that means that our new 1 over the new spring constant is equal to 1 over K1 plus 1 over K2, K1 again, because they're both the same thing. So that equals 2 over K1. So what we can do is we say, so we've got 1 over the effective spring constant is equal to 2 over that individual one. We can cross multiply and we'd get that the effective spring constant is equal to K1 over 2. Now that's just a nicer way of seeing it, and that's how that is derived. The formal relationship is this, which becomes a bit more unwieldy if you start dealing with springs that have different spring constants. That becomes a little bit harder, but ultimately the consequence is always that no matter how you combine things, your effective stiffness of the new spring system is always going to be smaller than the smallest. So then it's always going to be smaller than the smallest one there was possible in original things. So, and you'll actually see a derivation very similar to this when we do electricity and resistors when we measure them in parallel and things. But it's not a derivation you need to produce for the A level, but it is where it comes from, and you get the same sort of results. But essentially, as you add things in series, you end up with a smaller spring constant effectively. When you add them in parallel, you end up with a higher one. And it is possible to solve them for individual things, but often it's quite easy when they are identical because it just makes it a bit more easy. And there we go. That's a little bit of a sideways derivation for those of you who are interested.